Hi everyone, welcome back to a video on the Pythagoras channel, and today we will be going over basically all of just pure differentiation. So we're just going to be differentiating a bunch of functions today, and we're going to start with this one. Y equals the ln of the cube root of x minus 5 over x squared plus 4 to the fifth. And while this does look a little intimidating at first, we notice it's a natural log, so we can just use the log properties and split this up. So first, we can do y equals, first, since they're being divided, we can do ln of the cube root of x minus 5 minus ln of x squared plus 4 to the fifth. And now, there's a little bit more simplification we can do here. Cube root of x minus 5, this is really x minus 5 to the 1/3 power, right? So what that means is that this becomes y equals, and another thing we need to remember about our log properties, any power, we can just bring it out front. So this becomes y equals 1/3 times ln of x minus 5. And then this becomes, this 5, we bring it out to the front because of log properties. 5 ln of x squared plus 4. And then, what that means, having all this here, this means we're ready to just differentiate this. So now, differentiating y with respect to x, we just get dy dx. And this is equal to 1/3 times, and let's just apply the chain rule. This is 1 over x minus 5, and then we'd have to multiply this by the derivative of this inside function, which is just 1, so we don't even need to show that. And then minus 5 times 1 over x squared plus 4, but we have to multiply it by the derivative of this inside function, which would happen to be 2x. So, times 2x. Now, going down the line, you see dy dx. This is going to be equal to 1 over 3x minus 15 minus 10x over x squared plus 4. Now, we could try get a common denominator, but in the end, it would be rather messy, but we might as well try. So, that is an unsimplified answer. So let's just go over here and start to make our common denominator. So what we're going to need to end up doing is multiplying this by x squared plus 4 over x squared plus 4, and this times 3x minus 15 over 3x minus 15. So what this means is 1 times, we'll just write the first original, so 1 over 3x minus 15 times x squared plus 4 over x squared plus 4, and then this is minus 10x over x squared plus 4 times 3x minus 15 over 3x minus 15. So now what we need to do is we don't need to distribute the denominator. We just need to distribute over here. And what this leaves us is x squared plus 4 minus, and we'll leave this in parentheses for now, 10x times 3x is going to be 30x squared, and then 10x times negative 15, this is going to be minus 150x, right? And then all of this is over, and I'll take the x out again, the 3 out again, why not? So 3 times x minus 5 times x squared plus 4, and now subtracting these, we're going to get dy dx is equal to x squared minus 30x squared plus 150x plus 4, just reordering some terms, all of that over 3 times x minus 5 times x squared plus 4, and now finally we get dy dx equals negative 29 x squared plus 150x plus 4 all over 3 times x minus 5 times x squared plus 4. And this is your final simplified answer. Here, for our second problem, we have y equals the square root of the natural log of the square root of x. But let's not get confused. This square root is being applied to the entire natural log, which means we can't just bring it down as a 1/2. So, what we simply have to do is just start and apply the chain rule. So, dy dx equals, well, what's the derivative of the square root of something? It's 1 over 2 times the square root of that something. 1 over 2 ln, 2 root ln of the square root of x. But then we have to apply the chain rule. What's the derivative of this inside function? What's the natural log of something? So 1 over the just 1 over that something. So 1 over the square root of x. But then we have to multiply by the derivative of the inside. Well, what's the derivative of the square root of x? It's again 1 over 2 root x. So now what we have to do here is just multiply this out. So this becomes dy dx, excuse the form right there, I can't really see it, but this, and now here, what we notice is this is the natural log of the square root of x. We can bring that outside, so this actually becomes 1 over 2 root 1/2 ln x, and then, well, let's multiply these two together. 1 over square root of x times 1 over 2 root x. That's 1 over 2x, because the square root of x is multiplied together become just regular x. So this becomes times 1 over 2x. Simplifying further, dy dx equals, these twos multiply together. This becomes 1 over 4x root 1/2 ln x. And if we wanted to, we could actually move everything, or at least us 4 inside, if we want to get rid of this 1/2, which I think I do. So what we'll actually do is say dy dx, again ignoring the terrible writing. So moving this inside the square root would mean we'd have to make this a 16. So this becomes 1 over x, and then 16 times 1/2, that's 8. So 1 over x root 8 ln x. And that is what we would have for our final answer there. Here we have the equation y equals the natural log of the square root of 1 plus sine x over 1 minus sine x. And now what we can do is we first want to make sure we just split this logarithm. And that square root is actually basically to the 1/2, so we can take that all the way out front. And this becomes ln of 1 plus sine x. And then this, since it's being divided, we can do minus ln of 1 minus sine x. And now, differentiating both sides, we get dy dx to be equal to, and this 1/2 will just distribute as we go. So 1/2 times derivative of 1 plus sine, ln of 1 plus sine x, 1 over that. So 1 over 1 plus sine x times the derivative of the inside. Simply applying the chain rule, derivative of sine is cosine of x. Now subtracting, we have minus 1 over 1 minus sine x. So that's the derivative of this inner function, of the outer function. And then multiplied by the derivative of the inner function. Negative sine x, derivative of that is going to be negative cosine of x. Now, going along down, dy dx, this is equal to, and we're going to leave this 2 out here. We're going to bring the cosine to the top. So cosine x over 2 times 1 plus sine x, and then minus, and this net minus and minus, they actually multiply together and cancel. So we get plus cosine x over 2 times 1 minus sine x. And what we can actually see here is that if we were to get a common denominator, we'd get 1 minus sine squared of x on the denominator, which is cosine squared of x. So it actually might be rather useful if we did. So bringing it over here now, see that dy dx, this is going to be equal to cosine x times 1 minus sine x over 2 times 1 minus sine squared x plus cosine x times 1 plus sine x over 2 times 1 minus sine squared x. And what we should do here is we can distribute these, I believe, yeah? Or, let's do that. So dy dx equals distributed cosine x minus sine x cosine x. And also combining it in the same step, we get plus cosine x and then plus sine x cosine x. And what we see that these two terms even cancel out before we're done. Of course, this is all over 2 cosine squared x. Now, what we can do is, let's just write this again up here with all the terms crossed that we got removed. So this becomes cosine x plus cosine x over 2 cosine squared x. Now, cosine x plus cosine x, that's 2 cosine x. So let's write that. dy dx equals 2 cosine x over 2 cosine squared x. Cancel out the 2's. This becomes 1 over cosine of x. And what that actually means is that our derivative is quite literally just the secant of x. And that's pretty cool. We brought that whole square root function down to just one trig function. So one thing you want to keep in mind for problems like these is if you see something like if you multiply these together, you recognize a trig identity, then you might want to try to get a common denominator because it will get you a much simpler answer than whatever this would happen to be. Now for this problem, we have y equals x to the natural log of x. And for this, you actually have to use this technique to solve it. And it's called logarithmic differentiation. Since we have a function raised to a function powered, and that's the only time you're really going to need to use it, or when you have an excessive amount of product and quotient rules. What we need to do here, we can just take the natural log of both sides, right? So natural log of y equals, now we can bring this ln down, so we could just multiply it by the natural log of this, which is just x, so ln x times ln x. So here, what we can actually do is this becomes ln of y equals ln squared x, and there's a reason why I'm doing this. So now what we can do, this ln y, differentiating it, and since it's now implicit, we have to multiply by dy over dx. So, and then this becomes, the derivative of this, it's really just a double chain rule. So derivative of something squared is 2 times that something, so 2 ln x times the derivative of that something, and derivative of ln x is 1 over x. So now what we have is dy dx, and I multiplied the y to the other side, right? So first, what we're going to have is y times 2 ln x over x. But there's an issue here. We have a y here, but our original function is explicitly in terms of x. So we just substitute. We see y is already equal to x ln x. So that just means dy dx equals x ln x times 2 ln x over x. And we could do some things here since this is an over x. You could make this ln x minus 1, but it's really not necessary. We could bring this to the numerator as well. But at the end of the day, this is what we get as the final answer for that derivative. Here, what we have, a derivative where we have to use the product rule on an exponential and inverse trig. So what that means is we can really just jump right in and start differentiating. So dy dx, and using the product rule, we take the derivative of the first function, 2e to the 2x, because it's e to the 2x times the derivative and of the inside function. And then that is going to be times 2 this original function, arc cosine of x plus arcsine of x. Now we're going to add this with this original function, e to the 2x times the derivative of this inner function. And it's just adding two different functions. So what we have here is 2. And what we need to know about inverse trig derivatives is the co-function is exactly the negative of the original function. So the derivative of arcsine is 1 over the square root of 1 minus x squared. But the derivative of arccosine is just going to be the negative version. So what we have is negative 1 over the square root of 1 minus x squared. And how I like to differentiate these, or tell the difference between these and other inverse trig function derivatives, is that arccosine and arcsine, this is what they look like on a graph, and they just end there. They don't go anywhere much far. They don't go very far on the graph. So what you need to know is, since this function itself has a small domain, that means it's this derivative is the small domain one. So it's going to be arcsine or arccosine. And since it's a co-function, it's negative 1. Then we have plus 1 over the square root of 1 minus x squared. And as we can see here, we already have a common denominator. And basically what we can see this as negative 2 plus 1, and then divide by that denominator. So this is going to be negative 1 over this. But what we can actually notice here first is that we can factor out an e to the 2x. So this becomes, and don't forget dy dx is equal to this, dy dx equals e to the 2x times, and this becomes, and really we can distribute this too, why not? So this becomes 4 arc cosine of x plus 2 arc sine of x plus, we factored out this e to the 2x, so this becomes plus negative 1 over the square root of 1 minus x squared. And of course, we don't need a whole other step to write this down. We can just instead make this minus. So, and minus 1. And that's really it for our answer. We just have this. We don't need to worry about making a common denominator, because when we do that, it's meant to help us. This is not going to help us in any way if we get a common denominator. So really, we can call it a day here and acknowledge this as your final derivative for it. Here, we have another example of logarithmic differentiation. So we have a function to a function power, and inside that function is even a quotient rule. So this is actually going to help us quite a bit. So before you take a derivative, we can take the natural log. Natural log of y equals, and we can take this 2/3 x out front, and I'll just leave it like this for now. So 2/3 x times ln of 2x plus 1, and then minus natural log of 3x minus 5. And now what that means is we can multiply this out here and have two product rules, which I don't know why you would, or you could just leave it like this and have one product rule. So let's just do that. So this becomes 1 over y dy dx. This equals 2/3. We'll take the derivative of this, 2/3 x. That derivative, just constant multiple, it's just going to be 2/3, and then times this entire thing, ln of 2x plus 1 minus ln of 3x minus 5. And then this plus this original function, 2/3 x, times this derivative. So this is going to become derivative of natural log of something, 1 over that, so 2x plus 1, times the derivative of the inside, so times 2. And then this, we have minus 1 over 3x minus 5, derivative of 3x minus 5, that's 3. So now what we have is all these. So what we can just end up doing here is, we're going to have a very large parenthesis, is that dy dx is equal to y times, so we can have, let's distribute this 2/3 ln of 2x plus 1 minus 2/3 ln of dx minus 5 plus, and let's multiply out this x into both of these. You know this is going to have a 2 in the numerator, 3 in the numerator, and then 2 times 2 is 4, and then 2x plus 1 times 3, that's going to be 6x plus 3, and then minus 2 times 3 is 6 over, and then 3 times 3 is 9x, and then 3 minus times 95, minus 15. And really, that's almost our final answer, because now what we just need to do is replace this y with the original explicit function. So what we get is dy dx, excuse the writing, this is 2x plus 1 over 3x minus 5 to the 2/3 x power, not 2 over 3x, don't get that confused, times 2/3 ln of 2x plus 1 minus 2/3 ln of 3x minus 5 plus 4 over 6x plus 3 minus 6 over 9x minus 15. And that is your final answer. Technically speaking, we could actually have factored out the 2/3 to the front, and that would have saved us a little bit of time, or just made this look a little prettier. But that's really not too much of a deal. So that's our final derivative for this problem, question 6. Minor error of note, there should be an x here, but that is it. And technically it should also be up here. Here, what we have is pretty simple. What we're just going to end up doing here is we need to split this logarithm first, and we notice that it is an implicit problem, so we're not going to end up in something that's purely in terms of x. So let's just start with our first step. So to split the logarithm, always make sure you take out a constant multiple if you notice you can, because it will just end up 0, and 0 is nice to work with. ln of 3 is just a constant. Derivative of a constant is 0. And we can actually, while we're doing this, we can move this y down. So 2 ln y, because of logarithm properties. And remember, we haven't taken any derivatives yet, and this is equal to xy. So let's get started with this. Derivative of ln 3, 0. Derivative of ln x, 1 over x. Plus derivative of 2 ln y, that's 2 over y, times dy dx. Looks like a dg, but it's dy. Alright, and then we have derivative of e to the y. That's just going to be e to the y times dy dx. And this is equal to, we have to apply our product rule here. So xy, this is going to be derivative of the first 1 times y, plus original x times derivative of y. That's just going to be dy dx, or 1 dy dx, if you want to do it like that. And now, what this means is what we're going to need to do is we'll keep the dy dx terms on this side. So what we'll just do is we'll subtract 1 over x on the other side. But for now, we have 2 over y dy dx plus e to the y dy dx, and that's equal to y plus x dy dx minus 1 over x. And eventually we are going to need to multiply out the xy to get a common denominator, but let's just keep going as we are. So I'm going to factor out a dy dx in the same step as I move them over. So dy dx times, this is going to be 2 over y plus e to the y minus x, so they move it to the other side, and that's equal to y minus 1 over x. And now, just divide both sides, we get dy dx is equal to y minus 1 over x over 2 over y plus e to the y minus x. And now we just see we multiply this by xy over xy. I prefer multiplying it over here. I'm not sure why, but let's just write this answer up here. So I get that dy dx is now equal to this multiplies, which becomes xy minus y over, so the x, and then xy squared, actually, minus y, over these y's cancel out, 2x, e to the y, xy e to the y, minus x squared y. And what we actually notice is that on the top, we can factor out a y, and on the bottom, we can factor out an x. So let's just do that real quick. dy dx equals y times xy minus 1 over x times 2 plus y e to the y minus x squared. And this right here is our final answer for this implicit function. As I look at this problem for question 8, I noticed two potential things that we could do here. So we could either factor out this x and split this up, or we could just leave it and start differentiating using the quotient rule. But I think that I would like to try to simplify this equation in a way. So let's start. So this can really be, let's just write this. This is ln of x times 5x squared minus 7, correct? And that just means we can make this ln of x plus ln of 5x squared minus 7. So that's what I'm going to do here. So ln of x plus ln of 5x squared minus 7. And now this, ln of 5e to the 7x. Remember, you always have to take out this constant multiple as its own part of the log. So ln of 5, and that's going to be plus ln of e to the 7x. And one cool thing that we know is that whenever we have natural log of e to a power, these two cancel out, and this just becomes that power. So this actually becomes ln of 5 plus 7x. So now that we know this, we can just put this on the bottom here. So ln of 5 plus 7x. And let's just work our way down. So differentiating, we got dy dx. That is going to be equal to 1 over x plus, and let's quotient rule. Alright, so we have to square the denominator, ln of 5 plus 7x squared, and then over parentheses, and then we have to, again, we can write this ln of 5 plus 7x, and then times the derivative of this function, 1 over x, and then subtract that from ln of, and now we have to differentiate this function. This is just going to be 7, and then times this, times this original function, ln x, so 7 ln x. Apologies for the hiccup there. And then dy dx, this is going to be equal to, we're going to have ln, that's L5, ln 5 plus 7x over x minus 7 ln x all over ln of 5 plus 7x whole squared. And now what we want to do is just multiply this by x over x. So what we get is dy dx equals ln 5 plus 7x minus 7x ln x all over x times ln of 5 plus 7x whole squared. And that is our answer to question 8 using the quotient rule. What we have here is a very interesting problem, and y equals x to the pi to the x. Let's write that. So now to differentiate this is just a product rule, but the pi might throw people off, like, oh no, what do we do here? It's really just how you would treat any other number. So we'll say dy dx. Now we're just going to jump straight into differentiation. So let's keep the original function, derivative of the second. So derivative of the second, a to the x. Derivative of an exponential is a to the x times the natural log of a, where a is this base. So this is going to be pi to the x times the natural log of, not 5, pi. So that's our derivative for the second function, plus, now the derivative of x to the pi, so we remember our power rule, right? It's just, we bring this down and then subtract the power by 1. It doesn't matter what that power is, as long as the power itself is not 0. So we have pi times x to the pi minus 1. And then we just multiply that by the original of the second function, which is just pi to the x. And now, since everything here is being multiplied, I'm going to actually get rid of these parentheses, so just so it's a little clearer what we can factor out. So what we have here is a common factor of a pi to the x. So what we can do is we can just factor out this pi to the x. So we get that dy dx is equal to pi to the x times x to the pi ln of pi plus pi times x to the pi minus 1. And that's really it. We could actually make this x to the negative 1 over x, but then we'd have to get common denominator, and it's really just not necessary. So what we have here is our derivative. It's really just simple. It's just the numbers that might confuse you. So now that we're here, we have an implicit problem. So to solve that, we have to just differentiate both sides. So 2 dy dx equals, and now derivative of this exponential, e to the xy squared, but then we have to multiply with the derivative of what's inside here, which is a product rule. So let's start with x, and then derivative of the second function, 2y dy dx, and then plus 1 times y squared. So now what we have here is 2 dy dx equals, and what we're going to need to do is we're going to end up distributing this so we can get our dy dx term alone. So this actually becomes, not e yet, we're going to write 2xy e to the xy squared dy dx plus y squared And that, what we want to do here is, now we can just isolate the dy dx's. So that means 2 dy dx minus 2xy e to the xy squared dy dx equals y squared, meaning, factor out the dy dx. I don't want to waste space, so we can just divide it by 2 minus 2xy e to the xy squared. So the dy dx is really just equal to y squared over 2 minus 2xy e to the xy squared. And that's it for this one. Really just a simple implicit one where you just have to use the product rule and exponentials. It's like magic. The e to the xy squared just reappeared itself. My apologies there. There should be an e to the xy squared carry out. So y squared e to the xy squared. And that's just because I guess I have a skill issue, but it's fine. Now what we have is y equals arcsecant of e to the 2x. If this was secant, this one would be rather simple, but it's still rather simple because all we have is arcsecant instead. So you want to make sure you know the arctic derivatives. There's nothing we can do to simplify this, so let's just go ahead and differentiate using the chain rule. So derivative of arcsecant is 1 over the absolute value of what's inside, so e to the 2x, times the square root of this, e to the 2x, squared minus 1, and then times the derivative of e to the 2x, which is going to be e to the 2x, but the derivative of e to the 2x, the 2x in here, we have to multiply that, don't forget, so it's going to be 2. So now, what we get is dy dx equals 1 over, not 1, but 2e to the 2x over absolute value of e to the 2x times the square root of e to the 4x minus 1. So now what we can do here is e to the 2x is a number that is always going to be positive no matter what. So these absolute values, we don't need them. And now that we've removed the absolute values, they cross off. So what we actually end up getting is that dy dx equals 2 over the square root of e to the 4x minus 1. And that's what you get for that answer. So now what we have is y equals cotangent squared of pi to the 3x. So now let's go ahead and just differentiate this. There's no simplification we can do. So we're just gonna have to follow the chains of the chain rule. So the first thing we see, we have something squared, then we have cotangent of something, then we have a exponential, and then again we have a constant multiple times a function. So what this means is, first, derivative of something squared, it's 2 times that something, so 2 cotangent of pi to the 3x, and then now we multiply that by derivative of cotangent. Cotangent is, that derivative is negative cotesecant squared of this inside function. Then we multiply by the derivative of this inside function. And what that becomes is 3 pi to the 3x, because we multiplied it by pi to the 3x and then the derivative of this, 3. So this is going to be our final answer. We just have to move some terms around. So dy dx equals negative 2 cotangent pi to the 3x cosecant squared pi to the 3x and times pi to the 3x. And what we could do actually is move this instead of a 2, it should just be a 6. And if we wanted, we could move this exponential out front, but at the end of the day, it doesn't matter. So this right here is our final answer and the final answer for the last question of the video. So I hope you guys enjoyed this one. This one was just to review all sorts of derivatives, all sorts of derivative rules, and I hope you guys took something away from it. Thanks for watching.